Pleasure to be here. Sorry that I didn't get the memo to put a heat exchanger on the first slide. There will be heat exchangers, Duran, I promise. And I'm going to talk about how the cloud helps us to get to real-time design insights via cloud-native AI and physics simulation. That's a lot of words in there. We're going to unpack this over the next couple of minutes, and it's going to make more sense, I promise. But I did want to start with a very provocative picture that I'm going to show you now. And Duran already thinks, oh my God, what is he about to do? But it's not that bad. I want to use this little picture as a small analogy. We're all in computational design. We're all either driving simulation tools. We're sort of consumer of simulation insights. We all have, seen simulation images. And I sell simulation software for a living, so I feel like I can make this joke that is about to happen over the next minute. And so each time I see simulation results, our own, from other vendors, from simulation engineers, it reminds me of that embroidery, I think it's called, right? I thought it's knitwear, but of this embroidery, because on the front, the simulation result looks great, it's colorful, you can make design decisions, you know where this is going, right? You can make design decisions based off of it, but what most of the time in those situations is not talked about is the simulation process. Yeah. How did you get there? Yeah. How did you get there? And I really don't mean this for a specific tool, for a specific solver, for a specific vendor, for a specific engineer. It's really the nature of the beast, right? It's the nature of the beast that we're trying to predict physics on spatially complicated domains. And we have those spatially complicated domains being shaped in all forms. We've seen many different, modeling engines today, many different modeling paradigms. Physics, multiple nonlinearities, it's just nasty, right? And that is a single simulation. Typically, most of the customers we work with are larger teams. Take an automotive tier 1, automotive tier 2. They have many different programs that are they're supporting. Take a white goods manufacturer, many different product platforms. So you have all those engineers that you want to make design decisions, and at the same time, they should be able to just validate the design decisions as they go, but they can't, right? Because it's you layer on top all of this physics complexity. You layer on top user management, license management, data management, process management, and all the good things down here. I need to check, yeah. All of these things, right? And it's not to say that a single simulation solution or a single tool isn't good at anything. It's just like the nature of the beast as an engineering team grows, as a real-world engineering workflow is happening, as a real-world larger engineering organization is designing products, it gets tough, right? It gets tough to roll out simulation. And typically, what the response to this is a team starts to simply compromise and say, okay, look, this is so complicated, it's so nasty, we're not going to roll it out broad. We actually keep it central. We're going to manage this complexity central with a dedicated team of people. As a result, though, we're compromising simulation lead time, meaning because it's central, because only few people have access to it, as a result, most of the design engineers, program engineers, support engineers that are actually making design decisions on a day-to-day basis don't have access to real-time results. They're left there, we heard it earlier, and are waiting oftentimes for weeks to get their design generated until the design is simulated. And again, design generation, I'm going to show later a few example workflows with SimScale. Design generated could be done with any type of methods, any type of engine. It doesn't matter. Until it's simulated, there's a long simulation lead time. And I want to double click here once, and I'm not going to shake the table anymore. I want to double click once because oftentimes this is a bit mixed up with simulation cycle time. Simulation cycle time is really from where a simulation engineer, or for that matter, any engineer sits down and sort of, all right, look, let's get this simulated, right? And then all the nasty stuff around pre-processing, meshing, yada, yada, yada. So that is like, yes, there's time lost there, for sure. It needs technology, it needs good tools. But all the stuff before, this is Outlook, this is the simulation backlog, the simulation team's backlog. This is a process issue. It's not like necessarily a core simulation technology issue. It's an issue that arises from the fact that simulation has been deployed only always centrally in larger engineering teams. And so why is that, right? Let's double click. Why does it look like this? Why do most engineering teams deploy simulation this way? And typically when we start working with a customer, typically the simplified way of how we find a simulation stack to look like when we start working with them, it kind of looks like this. It historically grew, and so it started with a first simulation tool they rolled out a decade ago, maybe 2 decades ago, maybe just a couple of years ago for a particular physics, typically on some workstation for some user. They start adding some additional tools, maybe investing in a cluster. They start sort of, putting some homegrown automation around it, not the good stuff from Synera, right? we're friends. I'll mention them later again. Homegrown automation, some scripts. They dabble into CAD integrated CAE because they actually would like the design engineer to make design decisions. And then eventually for some peak workflows, some peak loads, they put stuff into the cloud. And that has created a lot of value, right? This is a process, this is a stack that has supported many design engineering decisions, many great products, aircrafts fly, cars drive, so that's good, right? But unfortunately, it's not very standardized. It's a heterogeneous software and hardware stack that is hard to scale. And so as a result, as we've heard before, think about the embroidery. It typically means that a central simulation engineer ends up running the simulations, driving the stack, right? And you can't deploy it. Because as engineers, we know if you want to scale something, you need to standardize. Tough to do with this. Because actually also like what we've heard in presentations before, hardware limitations, data, it gets tricky. And so the hours and seconds that we actually want all of our design engineers to be able to make design decisions instantaneously gets tricky. And so you see where this is going. This was the red slide, right? Now comes the blue slide, right? So that afforded us the chance, and that's sort of the story of SimScale. We thought about how should a simulation stack look like in order to enable engineering teams to use simulation aggressively, early and broadly in engineering processes, thereby make better design decisions earlier, and thereby really enable many of the novel workflows that we're seeing today, many new modeling paradigms. And it starts with the fact, from our point of view, that, which might be a bit biased because we're in the cloud, but from our point of view, it starts with the fact that user data process management can't be an afterthought. It needs to be baked in. We see many organizations today that actually have deployed really good tools, really good solvers, right? But they want to scale it, and they're struggling with the fact that they try to bolt on user data process management on top of it, which is tough. SimScale starts the other way around. So SimScale runs cloud native. It comes natively integrated. All HPC commissioning is done automatically. We're going to see it in a second. User data process management for broad deploys. And then the central simulation team always has access to everything that is happening. Right? So they have full visibility into how simulation methods are being used. And thereby, it's not just use it broadly. We heard earlier trust, right? Good point. So the simulation team needs to be able to monitor what's happening to ensure quality. On top of that, we integrate simulation technologies. And I also didn't, again, for the presentation before, I didn't clean this presentation from all the three-letter acronyms, so I want to pre-apologize for that. But we can see a bunch of different methods integrated here. We're going to see some in action in a second. That then end-to-end bundled to end-to-end physics workflows. We come from the CFD world. I have a CFD background. The second biggest part of our revenue is structural, and then thermal, and then EMAC. And all of that is then shipped really in a way that the customer wants to consume it. And that starts with, of course, most of our usage sits on our web-based GUI. We're going to see it in a second. I planned on a live demo while I'm not shaking the table. We're going to see how that works out. But also, and so that makes it easy for, we're going to see later a case study where when you want to deploy simulation to 100 engineers, a specific method, that's a huge pain, right? But if everything is vertically integrated, then sort of deploying becomes easy. So that is where the web GUI comes into play. And then the web API, meaning you have programmatically accessible physics. You can put it into third-party workflows, which then leads to the partner integrations. And yes, you guessed it, this sort of gets us to hours and seconds in simulation turnaround time. And as a result, program engineers can sort of innovate faster without the simulation team being the bottleneck. So let's see how this looks. Anna, there's the mission slide. I'm the CEO. I cannot make a presentation without stating SimScale's mission. So in a nutshell, we see our SimScale is not about one specific solver method or about one specific physics. SimScale is about how can we help engineering teams innovate faster by making simulation truly accessible at any scale. That means early, broad, while maintaining central quality control of an expert team that controls the methods. This is how it looks like. And everybody thinks, great, another simulation software, colorful pictures, right? We've all been there. So let's unpack this a bit. So what's special about this one? By the way, again, an e-motor, apologies. First of all, cloud native, meaning simscale.com, and you just log in and you're good to go. Again, of course, sounds fancy, sounds nice, but if you want to deploy a simulation to 100 engineers, it just becomes like, we know customers where it takes 2 months to commission a workstation there, right? So it's just like, it helps to drive adoption. Many products in the industries we work in are not governed by single physics, but are constrained by multiple different physics. And if you want a program, sometimes called platform engineers or application engineers, to own functional performance of the part of the assembly that they're responsible for, they're not going to learn 5 different tools. And so enabling them with a templatized way in a single application to drive many different simulations is sort of the reason why we have such a broad physics footprint. Any scale. Sometimes cloud vendors talk about unlimited scale, but we all know it's somebody else's computer. But it gives you more scale, so HPC commissioning is done automatically. That means you have high number of cores available, can run large model sizes, and at the same time, the number of simultaneous runs is practically unlimited. Let's stay with that. Real-time collaboration, again, it's 2024, right? Every other software has embraced that. Engineering software has not yet. We think, of course, it's nice to have it, but it really comes, if you want to drive simulation adoption to simulation novice users, it's, from our point of view, not a nice to have. It's important, because only that way they have direct access to a simulation engineer. Simulation engineer can go in real time into the project, can see what they are doing, can tweak workflows and the likes. And it really surprised me that AI wasn't such a big topic today. Maybe tomorrow, Duane? Tomorrow, okay. Sorry to screw with the agenda. So it is AI integrated. We're going to see more in a second what that means. But also here, the point is, because suddenly all simulation data, all design data, everything that is being simulated suddenly lives online in databases, in structured databases, right next to practically unlimited GPU computing power, just opens the door to a gradual path to AI adoption. Examples of what we're going to see in a second. So much to theory. Now let's see it in action, and then afterwards I'll show a few customer examples. Okay, nice. So the important thing about SimScale demos is always, this is a Google Chrome browser, right? So we're in a browser, we're starting with simscale.com, right? So imagine a scenario, tier 1, tier 2 automotive supplier, or for that matter, from an electronics OEM, a program, an application engineer wants to simulate a first version, responds maybe to an RFQ, to an RFP. In this case, a piece of rotating equipment, a centrifugal pump. We've seen that the user would start with a setup template. So we can see here on the left, this is a simulation method to predict the hydraulic performance of a centrifugal pump. My simulation team has provided me with that method. I go in, I bring in a CAD model. SimScale is CAD agnostic. In this case, we're bringing it in from as an XT file. We're assigning boundary conditions. Again, also here, I'm not touching any numerical setup. I'm assigning the flow region. No, that's the rotating region. And then I didn't need to touch mesh generation, etc., because my methods team has provided it with. And then I press and start, and my first run is going. And you can see in the lower left, this is already a performance curve. So we're simulating multiple operating points of that centrifugal pump in parallel. And of course, there's colorful pictures. And so as an application engineer, I can now, within the browser application, do a first performance check on this piece of rotating equipment. You get the idea, right? And again, if I'm not sure if I've used this method correctly, have I used the wrong template, do I want somebody else to take a look because I'm not sure if I've done this the right way, real-time collaboration is built in, so I can share this with my simulation expert, I can share it with a SimScale support team. Here's the application engineer going through a first design version. We can see 8 blades, 12 blades on the left. Same story, I make a design change, again, in whatever SimScale is authoring agnostic and whatever editing method you're preferring. And then the application engineer can already now sort of make a first design decision, right? Again, crucial in meeting, when a white goods manufacturer tries to meet all the deadlines in all the different platforms they are supporting, or when an automotive supplier tries to support multiple different vehicle programs at the same time and tries to sort of respond to all of those RFQs. The other speakers have done the logistics somehow better than me, right? Good. Then moving on. So that story right now showed us how the application engineer gets away from I'm waiting for the simulation team to respond to me with a simulation down to hours of me iterating through the first designs. That's still hours because that video was cut. It was a standard finite volume solve, so that takes about 30 minutes. Yes, it's in parallel, so all operating points in parallel, but at the same time, it's still on the order of magnitude of hours. So suddenly the engineering team starts producing simulation data in the cloud, and we've partnered up with Navasto. Matthias is somewhere in the crowd over there. All deep AI questions go to Matthias, just to preempt those AI. No questions anyways, so we're good. And so graph neural net method sits directly next to the simulation solvers. That means I can now take all of those simulations that my team runs, and that's parameter free. Right? I don't need a parametric model. In this case, admittedly, it's parametric. But I don't need my team to simulate, in some shape or form, a parameterized model. They can just keep on running centrifugal pumps, and I can start using that data, go into SimScale, sort of select the runs, and can train a graph neural net, physics agnostic, that now gives me a deep learning surrogate model that allows me now to do real-time predictions. And in the lower right, we can see a little link that says link for action. Right? So that's the second demo. We just chatted earlier about that it's tricky to do live demos in presentations, but we'll try. Right? So this is now live. If something doesn't work, it's totally the conference Wi-Fi. It's not the SimScale application. Right? Can we agree on that? Again, but here the story is that's the little rotating equipment, the centrifugal pump we've seen a second ago. And what we want to do is now my engineering manager, my team lead, my simulation team has trained the first AI model for centrifugal pumps. And so I can now go in and instead, and let's say I have a new version of my model. So this one, this 9-blade version. On the top left, we can see all of the different versions I went through, the geometries. On the left, we can see the simulations. And so what I'm going to do is, this is still an old geometry. And so what I'm going to do is, instead of simulating as we've seen it before, I'm going to select an AI model, turn the AI model on. We would need to talk about how AI models are versioned and managed and used. But in this case, I'm choosing the appropriate AI model. And what happens now in the backend is, instead of doing a full solve, it uses a deep learning surrogate and does an inference. And so within a second or less, we have a first result here. And I can see on the right an AI model confidence that tells me, is the geometry that I've just thrown against this AI inference, is that within the training space? Right? For a more technical explanation, Matthias. And now the good thing is, this is now parameter free, meaning I can go in and change things in the setup. So let's say I want to change the speed. So I'm changing the flow rate. And again, same story. Simulation setup has changed. Instead of a full solve, I get to invoke an AI prediction, and within a few seconds, I get an answer. That's conference Wi-Fi really sucks. Okay, there we go. Right. So this one, and then the last one before, I think you get the idea. Right? And the last one is, okay, this simulation setup now evaluated still an old version of my model. Now let's look at this one. This was the 9-blade one. So you can see I'm changing this, sort of assigning a new geometry to the simulation. The AI model is still turned on. You can see the volute looks a bit different, right? We have a different outlet. And I guess you can now guess what happens next. Again, bringing us back to the idea of, we talked in the earlier slides about it's tough to make broad, fast decision-making in engineering teams work. Right? And frankly, yes, there's a lot of sort of work that goes into actually build, the embroidery thingy. Training that model was not so nice. It took 8 hours on a GPU to train it. You need to, outlier, So it's not as smooth as it looks here. But because everything is in the cloud, because data is managed, because I have a digital thread between the data I used for training, I have that under control, right? And I can just gradually start rolling this out, gradually building such models in a practical way. I had a backup video, full disclosure, moving on. Good, and let's just wrap this up. I think I'm already a bit over time. All of what we've seen, we didn't talk a lot about methods, we didn't talk a lot about physics. So SimScale is a general purpose simulation platform with structural capabilities. It's an implicit finite element solver. Fluids, 4 or 5 different solvers in production, LBM, IBM, finite volume, thermal, conduction, convection, radiation, all of it coupled. And then a first low-frequency EMAC. Release happened late last year. And all of that sits orthogonal to the compute infrastructure, user data process management, as well as the AI capabilities. Good. And now just a few examples of how customers put this to use, because again, none of what I showed was an end-to-end workflow as we've seen earlier, right? Those really nice workflows where you have authoring of the geometry and then sort of the simulation in a loop. You said, oh, this is really just physics. Right? So whatever sort of the idea is, whatever you throw against it, you get at marginal unit cost a very fast prediction of how that product design performs. And it allows you to scale that within an engineering team. So this is Bühler, one of our customers from Switzerland, 11,000 employees, with the goal of cutting down 50% of their entire fleet of machines, 50% water consumption, 50% energy consumption, and 50% carbon footprint. And they wanted to deploy simulation very broadly, and within record time, deployed SimScale to 120 users. I need to validate record time if I can say the word. I haven't validated that yet. Next time, maybe have a more precise than record time. And also here, like everybody that manages larger engineering teams or thinks about engineering infrastructure, 120 engineers with workstations to do, thermal, CHT, fluid analysis, etc. It's a pain. So that is sort of really this cutting down lead times to hours. Then a good example of RLE, putting the AI capabilities to use. RLE, an automotive engineering service provider, and we heard about it earlier already in the Sanera presentation. They've built a foundational error prediction model on SimScale. So on the left, we can see a generic car shape being modulated. And then in the middle, we can see how all of this has been programmatically assimilated with a finite volume solve, or lattice Boltzmann solve, one of which. And then an AI model has been trained. And now they have a foundational AI model where with retraining that can now be used for responding to customer-specific models. Then traditional shape optimization, here with GEMU, a flow control and valve manufacturer. Again, shape optimization, we've heard earlier that optimization is still not being broadly adopted. We can see here, again, we didn't do the generation of the geometry. That's with our friends at Cases, at Friendship Systems. There, the geometry is being moduled, and you can see in the middle, this is the important piece here, 330 simulations, each of which an hour. So that gets tricky, right? And so that's why typically it becomes this large engineering project, and somebody needs to sit down and da. But because HPC management is included, it just becomes more accessible. NTOP, we've heard Brad and Marcus talk earlier. Also here, I've kept on begging Brad to not produce those very complicated geometries, but he kept on pushing. That was sort of not nice. It was a joke, right, Brad? Okay. We're excited about many new ways of how geometry is being authored, right, and specifically from a physics-driven perspective. And I think it's a great example where simulation plays like an important role in the geometry generation, and so we're excited about the collaboration with NTOP, equally with Sanera. We've seen earlier in the presentation how they, in another way, provide new ways for engineers and engineering teams to explore design spaces. Here we can see a conformal cooling example, something that would be very hard to do in a traditional history-based parametric CAD model. And Sanera can just push these models out. And then we can see that now suddenly we have this plethora of different models. All of them need to be validated and simulated. And this is where the integration with SimScale comes to play, and where we can very quickly produce, sweep the parameter space, sweep the design space, see what's a good outcome. And then also a shout out to the team at Octon, because they can't be here today. Another approach of how sort of physics-driven design is being done. And also here, simulation challenges, large models, complicated models. Excited about that one. And then the last one before I wrap this up. I was about to use another buzzword, trying to get around this buzzword. But generative engineering is already at the top, right? So past this point now. But I do think it's a very interesting application. KSB, a pump manufacturer, basically faced the challenge of, for reasons that are too long to explain, faced the challenge of needing to simulate a lot of their product portfolio. And instead of simulating all of it, because it was a regulatory change, it was a change in thinking and saying, okay, what if we can build generative model where we can actually put in the requirements for the centrifugal pump and produce a geometry out of it, right? And without now, again, going into the detailed method, we can see at the top here, it's about 1,000 simulation of a centrifugal pump run. Again, we're talking about serious compute, we're talking about serious effort if you want to pull this off with a standard stack. But because HPC commissioning is done easily, data management is done easily, you're not dealing with all of this gigabytes on your hard drive, etc. It just becomes possible, and they've built this generative engineering workflow. So just to wrap this up, SimScale is unfortunately not the solution to everything, but it is a novel way of using the cloud and deploying in a cloud-native and a cloud-first approach simulation methodologies, and thereby making them aggressively more accessible. And that is to more loads, to more users, while managing all data, while managing HPC, and thereby really enabling the next generation of computational design workflows that we're excited about. And we kind of feel like the folks in the basement getting the physics done. That's kind of the story about SimScale. And I realized everybody had this nice slide at the end introducing by name and the LinkedIn profile, and I really just have that. So I realized that might have been not the smartest thing, but we are headquartered in Munich, and our office is 500 meters south of the Theresienwiese, where the Oktoberfest is happening, so it's kind of still on brand, right? But my name is David. You can find me on LinkedIn or just on the internet. Next time I'll put it here.